So in today's talk, I'm really just going to give you an overview of the different opportunities and challenges we have around drone-based pesticide application in Australian plantations under the theme of today's workshop. Um, so just as a little bit of background, the use of drones is really in an upwardly trend in the Australian forestry, but generally the agriculture sector. Um, what we have seen, or what we are currently seeing, is that drones are offering very cost competitive solutions compared to helicopters. Helicopter operations for pesticide application tend to be rather costly. We also see that they're much faster than ground-based crews or ground-based application, whether it's a tractor or alternatives. And we see that we have increasing knowledge from our operators. Operators are becoming more confident with the technology, understand the technology a lot better. At the same time, we're also increasing that experience in forestry. And I think in Australia, the forest industry has really been on the forefront of this technology and really been very keen on the uptake. And so we do have a few years ahead of some other similar countries growing similar trees. And at the same time, we have a very industry-wide uptake of the technology. We're talking thousands of hectares being sprayed with drones on an annual basis. And so there is a really keen interest, and a lot of forestry companies are actually using it. And we have a very established networks of contractors to do that. Now, a few pros and cons of RPAS, or remotely piloted aircraft system, is what we call drones. So in terms of pros, they are very precise and we can do very targeted spraying, and we are flying a lot closer to the ground compared to helicopters. We can work in very steep or wet terrain that is either not accessible by ground-based teams or cause a lot of issues, especially when it also comes to objects. Drones tend to maneuver a lot better compared to helicopters. We reduce soil compaction, particularly compared to our ground-based or tractor-based systems. Drones can reach dense and tall canopies. Becomes really interesting when we're trying to spray our canopies for, let's say, insecticides, where we get a really good downwash of the drone into the canopy. We have a very quick setup and deployment. In most cases, we have contractors rock up with either a trailer, or the drone just fits in the tray of the truck or the bucky, and just goes from there. So it's a lot swifter than, for example, a helicopter, or a lot quicker in setup as well compared to tractor-based solutions. Certainly lower in cost, particularly for small or irregular areas. It becomes really interesting. And a good thing is that we have very good mapping technology on the drone as well, so we can map and spray at the same time, and offers us a lot of opportunity as well to record obstacles or objects while we're doing application. So it's really handy. A few cons is complex regulation, and I've highlighted it because it's one of the things that I'll talk about today. Licensing, particularly for the operators or the contractors, that becomes a bit more of a challenge. Limited label approvals for UAV use. So again, something I'll talk about today. As for now in Australia, the current labels do not allow for any UAV-based application specifically. However, we can use UAVs or drones or remotely piloted aircraft systems if aerial application is approved, but it falls under the same category then as helicopters or fixed wing. Drift risk, particularly in windy conditions. Now that's always the case, but then particularly compared to ground-based systems, we do fly higher than ground-based release. So that's probably one of the things that we need to kind of still be mindful of. But at the same time, it's probably a little bit of a lack of understanding of how the drift is created under different wind conditions. Restricted flight zones. Drones do have restricted flight zone, particularly under certain air paths or aircraft or airports. Visual line of sight is also a very stringent rule for us. So in Australia, for any of the agricultural drones, you must, as the operator, you must remain a visual line of sight of the equipment. So you must always see the drone. As you can imagine, in forestry and under taller canopies, that might become a bit of an issue. Smaller payload, so obviously the drones cannot carry as much liquid as a tractor or a helicopter, and even though there is newer technology out there that is increasing that volume of water that we can carry, it's still a fair way away from helicopter. So generally speaking, lower productivity, but what we now see these days is, especially with our more experienced contractors, they will have 3 or 4 drones flying at the same time with 3 or 4 pilots, and can cover the area rather quickly as well. Inconsistent equipment standards. It is obviously a very fast-moving technology. There is new drones coming out every year, probably at a quicker rate than everyone can keep up with. So it's just maintaining those standards for that equipment and the maintenance of it. That's also something to be mindful of. And then training pathways, also still developing. But as I was saying, through the work that we do, as well as the experience that we have in forestry, we are kind of on the forefront of that training, and we do offer a lot of that within the industry. So the talk I'll be talking, or the presentation I'll be giving today, sort of frames within the Forest Pest Management Research Consortium. So the Forest Pest Management Research Consortium is a collaboration between research partners, including the University of the Sunshine Coast and myself, and so also the forest industry and the chemical industry towards advancing pest, weed, and disease management issues. A lot of the work that we do is focused on pesticides as one of the main, management strategies still used by industry today. But at the same time, it also covers the application technology to apply those pesticides and the research. And that's really the focus of today's presentation. I guess also a bit of a comparison, the Forest Pest Management Research Consortium is kind of similar, or has a lot of similarities with TIPWG, so I hope that provides enough sort of context to who we are and what we do. And we have been doing spray drift research for the Australian forest industry. The reason we do it is to gain or maintain regulatory access to chemicals or pesticides that it covers both aerial and ground-based practices, and certainly more recently remotely piloted aircraft systems. As you can see, this is one of the field studies that we've done, people involved in it, quite keen interest. All the people you see on the photo are from different forestry companies. So everyone's just very keen to learn about the experience. Onto the more boring part, I guess. So for some people it's exciting, but it's the regulatory framework. In Australia, the regulator for chemicals is the Australian Pesticide and Veterinary Medicine Authority. In 2008, they released a document called the Operating Principle in relation to spray drift risk, essentially introducing new registrations to chemicals to spray drift risk assessment. What it means is that the chemical and the characteristics of the chemical were exposed to worst case spray scenarios, which then resulted in buffers that needed to be maintained. Or buffers that you cannot spray, or no spray zones. Now, in many cases, that resulted in very large or overly large no spray buffers and restricted access to pesticides. Pesticides came off market, use was no longer supported or became impractical. So here is an example, as you can see on the screen, of a typical label layout. So in this case, it's for boom sprayers. You would have different application rate, different release height, and then these are our buffer zones. So these are the areas of interest that we need to stay away from, and then usually this will specify a particular distance you need to stay away from depending on the input. Now, a little bit more about the spray drift risk assessment and the way it works. So there's 2 players involved, the applicant or the person who registers the product, as well as the APVMA or the regulator. The applicant provides information packages about the chemical that they are willing to register, and the APVMA will consider firstly the regulatory acceptable levels of that particular chemical or chemicals across those different sort of risk zones. And then they will develop the position curves of that chemical under different environmental conditions and go with the worst case scenario to then develop the spray drift risk assessment tool, and that will then eventually resolve into or end up on a product label. Now, a little bit more about these deposition curves, as that's quite an important piece of the research that we do as well. So this is what a deposition curve generally looks like. So you would imagine that at 0 meters here, so we have on the vertical axis, we have distance in meters. So at 0 meters is where we would either fly a drone or fly a helicopter or drive a tractor. This is where you spray. And generally we would expect that most of that spray deposit is deposited below or in our swath of the vehicle. And anything that's carried with the wind will travel downwards or downwind side. And so generally you have higher volumes that taper down as the wind drags them across. So this is the general deposition curve. What you can then plot on the y-axis is either your deposition or your RALs. So in this case, if you have, for example, a chemical with a particular RAL for a particular environment that is a 0.02 value, in this particular case, that would result in a 15-meter buffer. Yeah. So any value up to this you can accept, and so that becomes your buffer. Anything lower than that means the buffer becomes wider. Anything higher than that the buffer becomes shorter. Right. Now, for forestry, acceptable buffers are generally between 5 and 300 meters. That is acceptable, but generally, or what we really want is, particularly for aerial applications, is buffers around 40 to 50 meters. Anything above that becomes not supported, is not practical or uneconomical. However, what we are now able to do, and I'll talk about this in the next slide, but for use cases where these buffers are greater, like than or higher than 300 meters, we will make efforts to reduce drift potential by some of these changes that you can make, changing nozzles, adjuvants, product rates, and so on. So following on from that, in 2020, the APVMA released a new document essentially stating that we can now provide evidence of drift reduction technology in order to modify those buffers. So we will then update the drift instructions on a label or a permit and then recalculate the buffer zone. So here's a true example of an existing chemical quite frequently used in forestry. For aircraft helicopter application, we had buffers of 800 meters in natural aquatic areas and 400 meters in vegetation areas. We provided some of that research on drift reduction technology. In particular, we highlighted the use of AccuFlow nozzles for helicopters at different application rates, at different release heights, and at different wind speeds. And we were able to reduce these 800-meter buffers, for example, down to 25, and I think the maximum here is 120. So a lot less, and makes it a lot more operational for us. So this is now on a permit that we have established through the work that we do, and is actually operationally used. So that kind of brings me back to that same risk assessment. There is now a second stage here, and essentially it allows us to provide user-specific details in order to get a new product label or permit for a product. Now, the way that we do this, and this is part of the research that we are doing, is first of all, we need to understand what the droplet size distribution data is, and therefore we need a wind tunnel. So this is a wind tunnel. It's essentially a very big sort of tunnel. That's the best way to describe it, I guess. Wind blowing from this direction. You have a spray setup here. These are your tanks. You put on your particular chemical mix that you're interested in. On that sprayer is a single nozzle. So sort of if you were to look from above here on that wind tunnel, this is what you would see. So the left-hand side is the blue area, and then we will blow wind through here. Here is your nozzle. You will spray your tank mix through that nozzle, and that can be quite a specific one. And you can position that nozzle as you would on an aircraft or on a boom. And then that way, what we replicate is the condition under which we spray. And then we have a laser that essentially measures every single droplet that goes past it and measures how wide or what the diameter is of that nozzle. So what it looks like is what you see on this sort of graph. So we have the droplet diameter from 0 to 3,500 microns and a cumulative volume. The best way, so the different colors are different nozzle types. I'm not going into detail there, but essentially the more to the left, it means the more finer droplets you have. The more to the right, these curves are, the larger the droplets. The more vertical the curve is, it just means that all of your droplets, or most of your droplets, are within the same size category. The more diagonal or horizontal the curve goes, it just means that you will have more droplets in different size categories. So you'll have more here between 500 and 1,000, but also between 1,000 and 1,500, and so on and so on. Whereas when you look at, for example, the green lines here, all of your droplets are smaller than 500. General principle, not always true, but generally speaking, the smaller the droplet, the bigger the drift. So this is what we call the deposition, the droplet size distribution data, or the DSD. This type of data feeds into AgDisp. So AgDisp is a modeling software. You can set it up for your aerial or ground-based application, your helicopter. You provide your release height, your nozzles, the amount of nozzles that you have and how you have spaced them. The droplet size distribution is what you load into this platform, and then you can adjust your swap weights, your environmental or meteorological conditions, slope, canopy, everything that you do, and then you run a model. So this is millions of dollars of research supported by most chemical companies that resulted in this kind of platform, and was an important part of the regulation that we have today. From this modeling, what we then get is that is a deposition curve. So again, similar to what you've seen before, similar principle, and then it results into buffers. Now, some of the challenges that we have, and this is coming into, I guess, more like the need for the research, is that drones are not really compatible with the wind tunnel. We cannot fit a drone in it into this system. We also see that the orientation of the nozzles is different. So I've kind of just highlighted some of the things here, but generally on a boom, nozzles will face backwards or variations thereof, whereas in a drone, the nozzle will face downwards. So you'll be spraying down instead of that direction, or the downwind direction, I guess. And then particularly the newer drones have centrifugal nozzles. So I've spoken previously about the AccuFlow nozzles on the helicopter. This is what the AccuFlow nozzles look like. So you will see a vertical movement of droplets along the spray direction. But when you look at the centrifugal nozzles on most common new drones, you'll actually see a horizontal movement compared to the direction of the drone. So it's kind of perpendicular to the direction of the drone. So if you were to put this into the tunnel, it essentially will just spray liquid all around the edges of the tunnel, and becomes really difficult. In addition to that, the AgDisp modeling was primarily performed for helicopter and fixed-wing aircraft and the different turbulent models of those vehicles. Of course, drones have very different wakes and very different air turbulence around the vehicle, and so that modeling is not really accurate. So the best way, or the best we can do, is do field studies, and this is an example of what we have done. So we looked at 10 EXAG and 23 DJI field studies. So these are two providers of drones, agricultural drones. With the EXAG, they have those typical spinners, as I've showed you before, those centrifugal nozzles, whereas this particular drone that we tested still has the option to put in the normal nozzles as you would on a backpack or a helicopter or any other piece of equipment. And so you can change them. Some of the trends that we've observed is that most of our deposition under of the different runs that we tested contain spray up to 16 meters. So, and I'll show you this, but I'll talk about it later. And then drift was also reduced by lowering the release height. So the lower you are to the ground, essentially you remove the amount of wind that can take the plume or the smoke, the spray cloud away. So this is what it looks like. So at -3, this is the center of the SWAT. So you can kind of compare it with that black line here that goes horizontally. And then up to 0 meters is the deposition zone. So this is where we intend our spray to land. Anything beyond 0 is what we then call our downwind zone. And this is where the spray lands if the wind carries it off. So the few examples of different ones that we've done, and this is a typical layout. So you have the green box here is the spray zone, and then the red box is the deposition zone, where we then can measure deposition up to 100 meters. How we measure it is we utilize water-sensitive paper and mylar cards. Water-sensitive paper is used for droplet density and coverage, whereas mylar cards are being used for deposition. So we actually measure the fluorescence of that fluorescent dye, and this is one of the drones. I promise you, this is not blood. We didn't cut someone's hand off. It's just a fluorescent dye, and it just looks a bit awkward in the field. Moving on from the field study, we did actually sort of the opposite of what I said we couldn't do before in the wind tunnel, but we actually put some of these nozzles into the wind tunnel and to obtain droplet size distributions, and this is an example of that. And then we entered it into AgDisp, the modeling software. So those curves went in there, but we obviously had to modify AgDisp a little bit because we went with a helicopter, but we're obviously not flying a helicopter. So we had to reduce the rotor radius from a helicopter rotor to 4 essentially drone rotors. The vertical boom position, so with the drones, the booms or the nozzles are hanging under the vehicle, whereas a helicopter, they kind of hang behind the vehicle. The speed and the aircraft weight also had to be modified. We had to increase the rotor rotations per minute, so the propellers of drones spin a lot quicker than those of a helicopter, and we had to modify the positions of the nozzles as well. What we just wanted to see is whether, can we use the modeling software to kind of compare it with what we have been able to observe in the field? And this is some of the results of that study. So essentially the yellow dots are the field observed deposition of a particular run. The orange line is the fitted curve for that particular run. And then the black and the blue one are the AgDisp modeled one. So AgDisp modeled black means this is modeled under standard conditions, so very high winds, so 20-kilometer winds. So it's obviously causing a lot more drift, as you will see that tapers out. So the amount that we identify is a lot larger than the actual results. But then what we did is we entered the meteorological conditions from the field into AgDisp and not assumed a 20-kilometer wind, which is not what we measured in the field. It was more something like 5-kilometer winds. And we entered that, and then we wanted to see whether this curve was actually a lot more aligned with what we've measured in the field. And we actually were able to see a lot of correlation between the blue and the orange or the yellow lines, depending on the different runs that we've had. Unfortunately, our regulator does not accept this type of information as yet. They're still trying to figure it out themselves. But it is promising to see that, there is some potential. And that kind of sparked for us the next step of the research. So in terms of opportunity, and I'll finish my presentation with this, but we do have a PhD project going on. Our student is actually currently in the field doing some of his research, but we're comparing the field performance of 4, 6, and 8 rotor drones with the helicopter. We also want to understand whether the drift and deposition pattern of these vehicles changes on the different release heights and flight speeds, and then also understand what the efficacy is under varying canopy height. So is there an influence of trees on the deposition pattern? We wanted to have a better understanding of that as well. Another piece of work really important is adjuvants really have an impact on the tank mix, but the understanding is not there at the moment, and results have been quite inconsistent and counterintuitive in some cases. So this is an area that requires a lot more research. And on a broader scale, beyond what we are doing, new models are being developed for drones. Some of these similar models or platforms like the AgDisp are available for drones, but they're currently not in the public domain or used by the regulator, therefore. And then I guess one of the future sort of goals for us with drones is that we can actually utilize the vision detection and differentiation to be able to detect specific target weeds and then only spray those weeds rather than the entire area. So to make it more efficient, reduce the chemical use, and then really sort of tailor for that spot spray application. So we have a PhD student who's also working on that, but it's probably a little bit more forward thinking for us. Just to finish, I just want to thank all the consortium partners. We are funded through Forest and Work Products Australia. Especially want to thank our university to provide the research, and then as well all the consortium partners, including forestry and chemical companies involved. And as I said, thank you very much for your attention, and feel free to reach out to me offline. I didn't include any videos. I have lots of videos of drones being used in forestry in Australia. Unfortunately, I didn't include them as I wasn't sure how this was going to work. But yeah, happy to share these with you. So with that, I'll just end my presentation. I hope this was interesting to you guys. Have fun at the rest of the workshop. I hope it's interesting for everyone. I look forward to catching up with Jackie and the team to hear how it went. But apart from that, warm regards, and I'll hopefully see you next time. Bye.